Right after passing the Sun, 3I/ATLAS did something no natural comet should be able to do. It course-corrected, adjusting its path with pinpoint accuracy toward Jupiter's Hill sphere. The precision? 1 part in 26,000. After billions of miles through interstellar space, it's now locked onto a gravitational boundary 33 million miles from Jupiter, with a margin of error of just 35,000 miles. 230 observatories confirmed it. Is this physics we've never seen, or navigation? March 16th, 2026 will tell us. Let's dive right in. When 3I/ATLAS first entered our solar system, every astronomer treated it like just another interstellar visitor. Hyperbolic trajectory, check. Speed matched expectations, check. Direction looked normal, check. It was catalogued, tracked, and filed away as another rare traveler passing through without fanfare. Then it got close to the Sun, and everything changed. After Perihelion, the moment when it whipped around our star at maximum heat and gravitational stress, something remarkable happened. The object didn't just continue on its original path like every other comet we've studied. It adjusted, not randomly, not chaotically, with surgical precision. Here's what makes this so different. Yes, comets experience non-gravitational acceleration when solar heat vaporizes surface ice, creating gas jets that act like tiny thrusters. We've seen this thousands of times, but those jets fire chaotically. Comets tumble, spin, wobble. Their outgassing creates uneven motion in multiple directions that usually cancel each other out. The result? Messy, unpredictable paths with error margins measured in millions of miles. 3I/ATLAS did the opposite. The acceleration was weak but directional, and that direction, almost perfectly aligned to guide it toward Jupiter's Hill sphere boundary. Not sort of aligned, almost perfect. Let's talk about what 230 observatories worldwide are seeing right now. Not 1 or 2 facilities, not a handful. 230 separate teams using different equipment, different methodologies, different analysis techniques, all independently reaching the same unsettling conclusion. The object deviated from its gravity-predicted path. And with every new observation, every refined calculation, the pattern becomes clearer. 3I/ATLAS is heading toward a specific gravitational boundary with increasing accuracy, not decreasing. That's the opposite of what natural objects do. The precision? 1 part in 26,000. After crossing billions of miles of interstellar space, experiencing solar heating that can vaporize material, navigating gravitational turbulence from multiple planets, dealing with constant radiation pressure, it's approaching a zone 33.24 million miles from Jupiter, with an accuracy margin of just 35,000 miles. That's a 0.1% deviation after an interstellar journey. No natural comet in recorded history has ever demonstrated this level of controlled approach. Not Oumuamua. Not Borisov, not any of the thousands of comets humanity has tracked. What makes astronomers pause isn't just the precision itself, it's the timing. The course correction didn't happen gradually over months. It occurred sharply after perihelion, precisely when and where it needed to happen to reach this exact boundary. Think about what that means for a moment. If the adjustment had occurred earlier in its approach to the Sun, it would have been too soon. The object would overshoot or undershoot by millions of miles. If it had happened later, after moving away from the Sun, same problem. Wrong trajectory, wrong timing, wrong arrival point. But it happened at the optimal moment. The single best time in the entire journey to make a correction that would guide it to Jupiter's Hill sphere edge. Space agencies know this timing window intimately because they use the same principle when planning spacecraft trajectories. You make course corrections at specific points, usually near massive gravitational bodies, to maximize efficiency and precision. 3I/ATLAS followed that exact playbook. Interstellar objects are messy. They enter our solar system tumbling unpredictably. Their surfaces are uneven, reacting differently to sunlight across different areas. Small changes in heating push them in multiple directions simultaneously. This chaos is why astronomers build in wide error margins when predicting their paths, sometimes millions of miles of uncertainty even with our best models. But 3I/ATLAS keeps defying that expectation. Instead of growing uncertainty over time, every new observation narrows the error margin. The accuracy improves. The trajectory stays clean and stable in ways that don't match the noisy, erratic patterns we see in natural cometary motion. When researchers modeled what 3I/ATLAS would need to do to reach Jupiter's Hill sphere, they calculated the exact strength and direction of thrust required. The actual observed acceleration matches that calculation almost perfectly. If the push had been 5% stronger or weaker, the object would miss the boundary by millions of miles. If the direction had been off by even a few degrees, same result. Complete miss. But it wasn't off. It was nearly exact. Jupiter's Hill sphere isn't just empty space. It's a gravitational boundary where Jupiter's pull becomes stronger than the Sun's. Cross that invisible line, and the dominant force controlling your motion changes instantly. Most natural objects never hit this boundary because their chaotic paths either pull them deeper into Jupiter's gravitational well or keep them far outside its influence. Here's what most people don't realize. This boundary is razor-thin. A small shift in approach angle or velocity creates completely different outcomes. When an object crosses into the Hill sphere, Jupiter's gravity can capture it, accelerate it to extreme speeds, or eject it from the solar system entirely. Outside the boundary, motion is stable and predictable. Inside, everything becomes dynamic and unpredictable. This is why space missions treat Jupiter flybys with extreme precision. Even a few thousand miles of error can shift a spacecraft's trajectory by millions of miles later. For a natural object to approach this boundary with 1 in 26,000 accuracy after a course correction at the optimal moment. That's not just rare. That's something we've never seen before. Scientists are wrestling with this because none of the standard explanations fit cleanly. Some point to observational error, suggesting early measurements created a false pattern. But here's the problem. With 230 observatories now confirming the same trajectory, the error margin keeps shrinking, not expanding. If this were measurement error, we'd see increasing disagreement as more data came in. We're seeing the opposite, growing consensus with tighter precision. Others suggest natural outgassing could explain it. Perhaps solar heating created gas jets that happened to align perfectly with surface cracks, producing organized thrust in one consistent direction. For this to work, though, the jets would need to fire at exactly the right strength and angle for an extended period. Even small variations would send 3I/ATLAS millions of miles off course. We're talking about winning the cosmic lottery, right composition, right structure, right rotation, right heating, right timing, all aligning perfectly. There's also the coincidence argument. The solar system has existed for 4.6 billion years. Countless interstellar objects may have passed through undetected. Maybe a few randomly came near Jupiter's Hill sphere by chance, and 3I/ATLAS just happens to be one we caught. But when you calculate the probability of hitting this specific boundary with this level of precision after a course correction at the optimal moment, coincidence becomes harder to accept. Then there's the possibility that keeps researchers awake at night. controlled or semi-controlled motion. This doesn't automatically mean artificial intelligence or alien technology. An object could have unique internal structure or chemical composition that allows it to respond to sunlight, gravity, or thermal stress in ways that produce directional thrust. Nature has surprised us before with mechanisms we didn't expect, but the level of precision here challenges even that explanation. The uncomfortable truth is that each explanation requires either extraordinary luck or physics we don't fully understand. And right now we're watching something that shouldn't be possible under our current models of how natural objects behave. What happens when 3I/ATLAS reaches Jupiter's Hill sphere boundary will tell us more than months of speculation. The competing gravitational pull between Jupiter and the Sun creates intense tidal stress at this edge. Many comets crack when exposed to rapid gravity changes. If 3I/ATLAS fragments, we'll see inside it for the first time. Layers, cavities, materials, internal structure no telescope has penetrated. This would answer questions about how it formed in another star system while raising new ones. How did something this structurally sensitive survive billions of miles of interstellar travel? Some researchers are watching for something else entirely. If 3I/ATLAS releases smaller objects or particles as it slows near the boundary, that behavior would be remarkable. Natural objects shed fragments sometimes, but doing so at a precise gravitational transition point would suggest responses to environmental conditions we haven't seen before. Any pattern in how those pieces move, any organization in their trajectories, would fundamentally challenge what we think interstellar objects can do naturally. The third possibility might be the most revealing. If 3I/ATLAS shifts trajectory once it reaches Jupiter's gravitational domain, turning toward a new path, decelerating further, or entering temporary orbit, we'd have evidence that its motion involves more than random forces. Even a slight adjustment at this boundary would become one of the most important observations in the entire investigation. Here's what keeps this story alive in scientific discussions worldwide. Natural comets don't demonstrate spacecraft-level precision across billions of miles. They don't self-correct at optimal moments with minimal energy. They don't aim for gravitational boundaries that even human engineers struggle to reach with deliberate planning. The data is real. The observations are confirmed by hundreds of independent sources. The precision is measurable and unprecedented. What's missing is a natural explanation that accounts for all these factors without requiring chains of extraordinary coincidences. Whether the answer involves exotic physics, unknown natural mechanisms, or something we haven't yet considered, 3I/ATLAS is forcing a question that matters. What maintains consistent, precise motion across interstellar distances with this level of accuracy? March 16th will give us answers. Until then, we're watching an object that behaves like it knows exactly where it's going. And that's what makes this story different from anything we've tracked before. So here's what we know for certain. An interstellar object executed a course correction after passing the Sun, now locked on to Jupiter's Hill sphere with 1 in 26,000 precision. 230 observatories worldwide confirmed it. The timing was optimal. The accuracy is unprecedented. And on March 16th, 2026, we'll see what happens when it reaches that gravitational boundary. Will it fragment, release something, change direction? The answer will rewrite what we thought possible for natural objects traveling through space. The data is verified, the precision is measurable, the implications are undeniable. Whether this is physics we don't understand or something navigating with purpose, we're witnessing something that's never been documented before. If you want to stay ahead of this story, here's what you need to do. Hit that like button right now, subscribe to Galactic Breaking News, and turn on notifications so you don't miss the Jupiter encounter coverage. Drop your theory in the comments. What do you think is guiding 3I/A TLAS? And share this video with someone who's been following this object as closely as you have. March 16th is 98 days away. We'll be covering every moment. See you in the next one.